Secrets, secrets, secrets. They have always intrigued humankind from time immemorial, which is why we will go to any length and spend billions of dollars to uncover them. One of the most expensive secrets humans have not been able to resist is up there when you raise your head to the sky, the universe. Ever since their discovery, black holes have fascinated humans, and at the latest attempt to unlock their secrets, we have sent the mighty James Webb Space Telescope JWST to space. Join us as we dive into the James Webb Space Telescope's terrifying discovery of black holes that changes everything. How far is too far to seek information? How far into the past can you dig for something before you give up? Humankind is about to set new world records in that regard. We have always been so obsessed with why we are here that we pause what we are doing to seek the answer. Now the answer is taking us to deep space and billions of years into the past, and we have a potent weapon to aid us in the search for the meaning of life, the James Webb Space Telescope, or JWST for short. The JWST is not the first space telescope humans have put in space to spy on whatever or whoever is out there. We already have the Chandra X-ray telescope launched in 1999 and the most powerful X-ray telescope that examines the X-rays emitted by some of the universe's strangest objects, including quasars, immense clouds of gas and dust, and particles sucked into black holes. But of course, there is the granddaddy and most beloved of space telescopes, the Hubble, which has been faithfully serving as our eye in space from its position in the Earth's orbit since 1990. It has shed light on the vast scale of the universe, the life cycle of stars, and the formation of galaxies. So what does the JWST bring to the table that we do not already have? The truth is that the JWST is the scientific successor to Hubble because its science goals were motivated by results from Hubble. At this point, it is important to point out that the JWST is not the replacement for the Hubble, but rather a successor that serves a different purpose. The Hubble and JWST also differ on how they work. First, the Hubble stays on a close orbit around the Earth, about 350 miles above the Earth, while the JWST is going far into space. Its final location is 1 million miles away at a point known as the second Lagrange or L2 point. In addition, while the JWST will primarily look at the universe in the infrared, the Hubble studies it primarily at optical and ultraviolet wavelengths, although it has some infrared capabilities. The JWST observes primarily in the infrared and has 4 science instruments to capture images and spectra of astronomical objects. These instruments provide wavelength coverage from 0.6 to 28 micrometers or microns. The infrared part of the electromagnetic spectrum goes from about 0.75 microns to a few hundred microns. This means that the JWST instruments work primarily in the infrared range of the electromagnetic spectrum, with some capability in the visible range, particularly in the red and up to the yellow part of the visible spectrum. In terms of size, the JWST is the largest space telescope we have ever launched, so much so that the team had to fold it up to fit it on the launch rocket. It has an approximately 6.5-meter diameter primary mirror, which gives it a significantly larger collecting area than the mirrors available on the current generation of space telescopes. Hubble's mirror, for example, is much smaller at 2.4 meters in diameter, and its corresponding collecting area is 4.5 meters square. This gives the JWST around 6.25 times more collecting area. The JWST has a significantly larger field of view than the NICMOS camera on Hubble, covering more than about 15 times the area. It also has significantly better spatial resolution than is available with the infrared Spitzer space telescope. One of the most distinctive features of the JWST is the sun shield that is meant to keep it at the extra cold temperature that it needs to work. A cold temperature is required so that there will be no interfering infrared emissions. This shield is one of the most complicated objects ever launched into space. It contains 5 layers of specially made materials that must be positioned accurately for the system to work. Each layer is about 21 meters in length and 14 meters at its widest point. To get how wide this is, just picture Serena Williams playing tennis on a standard court. These shield layers were so large that they had to be folded up and then unfolded as the telescope journeyed to its permanent abode. The Hubble has been visited by humans for repairs, but that is not even remotely possible with the JWST, at least for now. So everything had to be just right the first time. NASA estimates it has enough fuel to function for 10 years, after which, if possible, it could be refueled, and if not, will remain as a silent $10 billion century in outer space. However, within that 10 years, the JWST will deeply expand our knowledge of why we are here and how we got here. Our story of the universe began about 14 billion years ago with what scientists have called the Big Bang. Clumps of lurid blues and purples known as cosmic microwave background radiation reveal minute variations in temperature and density. This first meaningful snapshot of the early universe, about 400,000 years after the Big Bang, was taken in the 1990s using NASA's Cosmic Background Explorer satellite. But thanks to the JWST, we will now peer back in time and space to see the very first stars and galaxies that formed from hot, dense clumps of gas and dust. But what will we see? This is where it gets really exciting. Black holes are famous for their seemingly insatiable appetite. They swallow everything around them. If you favor sci-fi films, you would have seen them eating up the bad guy spacecraft in the grand finale. However, black holes are real. They swallow everything because they are compact, dense concentrations of matter in space, a region with such a strong gravitational pull that not even light can escape. A stellar mass black hole with a mass of tens of times the mass of the Sun can likely form in seconds after the collapse of a massive star. Relatively small black holes can also be made through the merger of two dense stellar remnants called neutron stars. A neutron star can also merge with a black hole to make a bigger black hole, or two black holes can collide. Mergers like these can make black holes quickly and produce ripples in space-time called gravitational waves. Scientists worldwide have been observing Sagittarius A, the supermassive black hole at the center of the Milky Way galaxy. They know the black hole exists, evidenced by its gravitational effects, but imaging it has proven elusive. Sagittarius A won't be the first black hole to be imaged. In April 2019, a group of more than 200 astronomers from all over the world unveiled the very first image of a black hole. They used the Event Horizon Telescope, or EHT, an array of radio telescopes to image the black hole at the center of the galaxy Messier 87, or M87. The EHT team compiled the image from 8 telescopes on 5 continents, working over an observing period of 7 days. M87 is located about 55 million light-years from Earth and weighs in at about 6.5 billion times the mass of the Sun, much larger than Sagittarius A. However, scientists are more interested in Sagittarius A being the center of our galaxy. The JWST will now spearhead the effort to image this black hole. It is located about 27,000 light-years from us and is 4 million times the mass of the Sun. So what makes Sagittarius A challenging to image, even though it is closer to us and smaller than M87? Well, the first image of a black hole revealed the silhouette of the black hole surrounded by a glowing halo of fiery gas. Nicknamed a ring of fire, the hot gas formed a circular shape around the black hole's event horizon. In the process, it confirmed predictions of what a supermassive black hole looks like. However, the view of Sagittarius A is also distorted by plasma, or cloudy ionized gas, that stands in the way between ground-based telescopes and the black hole as they look through the plane of the Milky Way galaxy. Sagittarius A also has flickering flares in the material surrounding it, which alter the pattern of light on an hourly basis. Sagittarius A is the only known supermassive black hole to have this kind of flare. While that has made capturing an image of the region very difficult, it also makes Sagittarius A even more scientifically interesting. The JWST is our best shot at uncovering the secrets of Sagittarius A. Apart from its powerful capabilities, the telescope is positioned in such a way that will give it an uninterrupted view of Sagittarius A throughout its cycles of flaring and calm. That's because, as stated earlier, the JWST will be occupying a position 1 million miles away from Earth at the Lagrangian point 2 gravitationally stable point. The L2 orbit is just perfect because it ensures that the telescope can stay facing away from the Sun at all points, protecting itself against the light and heat of the star. JWST's orbit also keeps the telescope out of the shadows of both the Earth and Moon, allowing it to have an unobstructed view of the universe for the entire duration of its orbit. In contrast, the Hubble Space Telescope goes in and out of the Earth's shadow every 90 minutes, affecting its output. Using multi-wavelength observations of Sagittarius A by EHT, Webb, and other telescopes will help scientists better understand the mechanisms that govern these cosmic beasts. One of the things that scientists want to understand about Sagittarius A is what sparks its flares, how they peak and later dissipate. This not only helps scientists study black holes, but it will also give them better insight into the Sun and its flares. However, NASA did not send a $10 billion telescope to look at a single black hole. The JWST will also tell how new stars in our galaxy are born. Actually, stars are born in a massive cloud of gas and dust known as a nebula. And over the years, the Hubble Space Telescope has captured stunning images of these stellar nurseries in the Milky Way. But because nebulas are so dusty, it's hard to see what's happening under the clouds. However, the JWST is even more powerful in the infrared range. It will see even deeper into the dark splotches in the image on the right. The images will be stunning. The JWST will also tell us if there is another planet like the Earth out there. Knowledge of planets outside our solar system is relatively recent. It wasn't until the advent of planet-hunting telescopes that survey the sky, such as the Kepler Space Telescope and its replacement, the Transiting Exoplanet Survey Satellite, TESS, that we detected thousands of planets orbiting alien stars. Some of these planets are unlike anything in our solar system, such as planets known as sub-Neptunes, larger than Earth but smaller than Neptune. Other planets are similar in size to Earth and orbit their sun's habitable zone, the point at which temperatures might be suitable for hosting life. The JWST will open our eyes to more of the secrets of the universe. Let's hear what you think of the JWST in the comments section below.